Good evening. In our last class, we just started with the DFT and we were about to start with the computation of the total factor matrix. Okay. So today we will start with this total factor matrix. So I will be giving you the example with the 2-point and 4-point total factor matrix, and the same method it goes for the other matrices. Okay. One important thing you should keep in mind is that when we are talking about the DFT, usually we talk about this DFT in the order of or in the multiplication of 2. Okay, 2, 4, 6, 8. In this way we should go. Okay. Another important thing is that later on we will be going towards the FFT, which is a way to implement DFT. Okay, and in that case we consider DFT in the format of to the power n. That means we will go for 2, 4, 8, 16. In this way we will be having the FFTs. That means 2-point FFT, 4-point FFT, 8-point FFT, 16-point FFT. In that way it's in the case of DFT, we usually go in the form of in the multiples of 2. Okay, so that means we will be having the even numbers when we try to do the DFT. Okay, now when we start with DFT, the computation of the total factor matrices, it happens in the S plane, that is the Laplace plane. Okay, so what is that Laplace plane? We are still not in the Laplace domain, but I will just give you an example wherein we are having this sigma in the x-axis and in the y-axis we are having imaginary j. Sorry, it is not the in Laplace plane it is j omega. Here it is just the complex plane. Okay, sigma and j. Okay, so within this complex plane we are having this unit circle. Unit circle means a circle whose radius is 1. Okay, a circle whose radius is 1, and usually what we do, if we have to calculate the angles, we usually go in the anti-clockwise manner, right? So say 0, 90 degree, 180 degree, okay, and so on. But since in the total factor matrix we are having e to the power minus j omega, here we have to go in the clockwise direction. Okay, so when we are talking about 2-point DFT, and if you consider this unit circle, 2-point means the first point should always be at 0. So where should be the second point? Second point should be at pi. Okay, and we know that we have to move in the clockwise direction. So if you look into the total factor matrix, what we will be having, n equals to 0, 1 and k equals to 0, 1. So this is W02, 0 multiplied by 0, and 0 multiplied by 1, W02. Similarly, this one will be also W02, W12. Okay, so what is the values now? W020 means this value is 1, e to the power this is 2, and then we are having nk value. If it is 0, that means Wn it becomes 1. This is 1. At 0 it is 1, 1, 1, and over here 1, 2. So this was the 0th point. First point is at minus of 1, right? What is this point? If it is a unit circle, this is minus 1. So we are getting minus of 1. Okay. Now let us take the example of 4-point DFT. In the 4-point DFT, we have n equals to 0, 1, 2, 3. Here also 0, 1, 2, 3. Accordingly, if you see, we have put the value this WNK values W000, 000, 1, 2, 3, 2, 4, 6, 3, 4, 3, 6, 9, and our capital N is 4. I did not put it. Okay, so everywhere it should be 4, but for the sake of my yeah, comfort, I did not put this force. Okay, so we are having this total factor values. Now we have to compute what are the values of this one. So what we have to do, we have to divide this unit circle into 4 parts. Okay, into 4 parts. When the capital N was equal to 2, we divided the circle into 2 parts. So first part was at 1 DC frequency, then 360 by 2 is 180. So that means at pi radians we had another point, so that would have been -1, right? In the case of 4-point DFT, we have to divide this circle into 4 parts. That means we are having values of 0, then 1. At every 90 degree we will be having the points. Okay, 360 by 4 is equal to 90. That means at every 90 degree we will be having the point 0, then 90, over here 1, then again 90 degree. If we move from here, we will be getting 2. Again if we get to the third point, it will be 3. Then again we come back to the same point. So 0 and 4, these are same. Okay, then 1 and 5, it would be same. Then 2 and 6, it would be same. Then 7 and 3, it would be same. Then after 7, where will be the 8 point? 8 point will be at the location of the 0th point. Okay, so in this way, if you see our these 0 nk values, it will be going on. Okay, so what is happening? What is the value at 0? We are having the value of 1 at this point. At nk value 1, but value we should be having -j. Okay, at nk value 2, what value should we be having? -1. For nk value equals to 3, what value should we have? J, right? So it will go in this form. So if you see this row and this column, they will be having the values of 1 because nk value is 0. So 0 is 1. Next is, if you see w of 1, where we have w of 1? At -j. See, we have put the value of -j. Okay, then w2 -1, w3 j. Okay, so in this way you will be filling up all the values. Okay, then for computing the conjugate of total factor, so what we should be having? 1 1 1 1 1 minus j, it will be converted to j, then -1 minus j. Okay, then 1 minus 1 1 minus 1, then 1 minus j minus 1 j. So this will be the conjugate value. Clear? Any doubt? Okay, good. So whatever I told, these are there. Then if I ask you to calculate the endpoint 6-point DFT matrix, total factor matrix, what you have to do? You have to divide this circle into 6 points and you will be getting these coordinates. If you compute it for 1 point, see at all other points the values are just the conjugate. Okay, so you just have to calculate only 1 point for the 6-point matrix. Okay, so again you will be making this matrix and just you have to plug in the values to get the 6-point total factor matrix. Any doubt? No? What you didn't understand? It's as simple as that. You are having in this complex plane the real value and imaginary value. You should always start at 0. So for a 2-point DFT, 360 divided by 2, 180. So the second point will be 180 apart from this first value. So it should be here. Okay. So what is the value of this point? Magnitude, it is a unit circle. What is the coordinate value? 1 0. So value is 1. 1 plus j 0. So value is 1. 1 plus j 0 na? So value is 1. At this point, minus 1 plus 0. Value is minus 1. Now if I have to calculate this total factor matrix for 4-point DFT, 360 by 4, 90. This was my first point. That means the 0th point. Then point 1 should be here because it should be 90 degree apart. Then second point, it is at 180 degree. Then over here, if you again go 90 degree, you will be getting the NK value 3. If you get the NK value 3, you should be here. Then again, if you have to compute the NK value, total factor value for this NK equals to 4, you will be here because it should be 90 degree from the third value. Then 5, then again 6, 7, 8. In this way, you should be rotating on the unit circle. Okay, you should be rotating on the unit circle. Okay. So how to find out these values? It's pretty easy, right? Similarly, if you go for the 6-point DFT, you need to divide this circle into 6 points. How much it is? 60 degree. So you should be getting at 60 degree angle this thing. Then from here again at 60 degree you will be getting another point. From here again 60 degree you will be at pi. Okay. Then again 60 degree somewhere here, 60 degree over here. Okay. So in that way you will be going. So see 0, 1, 2, 3, 4. Then say 5. Yeah, 5. Then 6, 7, 8, 9, 10, 11, 12, 13. In this way it is going, and we went up to 25 because in the total factor matrix we will be needing values up to 25. And I hope you should be able to compute these coordinate values. Yes or no? Simple trigonometry, 11, 12 trigonometry. You should be able to find out or not, right? So once you are able to compute this, so you will be getting these coordinates, and once you get the coordinates, just see 0.5, we are on the positive axis, these are there, and this value is C, it is in the positive j 0.816, and here it is minus j 0.866. Pardon? True. Yeah, exactly. So, yeah, that's true. So there is a mistake here. No, it should be positive, na? We are in the positive real axis, na? This is real, na? So this is negative. These two are negative. This is real, na? Sorry. So J factor will be negative because we are in the negative J axis, but we are in the positive real axis. Na? Yeah. So in this way, you just have to put in the values. Okay. So next, let's see one example. 2-point DFT will be looking into this. So xn equals to 2 0, and we need to keep in mind that input and output both are of same length. Both are of same length. Okay. So total factor, and if we are given with say xn equals to 2, so we have got this signal, but we, as I told you, we can do 2-point DFT, 4-point DFT, 6-point DFT, 8-point DFT, like that. We can go in the even numbers. So we have to pad the signal with 0. So if I put 1 0 over here, so it does not change the signal. If there is nothing, that means it is your 0, the value is 0. Okay. So this addition of 0, it is called padding with 0. Okay, 0 padding or padding the signal with 0. Okay, so xn equals to 2 0. So this is our 2D DFT signal. Here in the last class I told it will be given in this format, but you have to put it in the column format. So this is 2 by 2 matrix and this is 2 by 1 matrix. So if you do the matrix multiplication, what should be the size? The size should be 2 by 1, right? So 2 rows 1 column, so you get 2 rows and 1 column, and if you compute this, you get 2 2, and this is your frequency domain signal, which is given by capital X of k equals to 2 2, comma 2. Okay, so this is our frequency domain signal. Now if I ask you to plot this, so how you should plot it? This should be k, this should be modulus of x of k, and 0, we are having 2, and 1, 1, 2, at 1 should be having 2. Okay. Now I need to perform this what you call IDFT. That means I need to get back from x of k to the x of n. So what I said, the equation would have been 1 by capital N multiplied by conjugate of total factor multiplied by x of k. Am I right? So 1 by n is 1 by 2 multiplied by conjugate of the total factor. Here there are no imaginary value, so the matrix remains the same, multiplied by x of k. Okay. Again, using the same analogy, if you calculate, you get back to this xn equals to 2 0, which was our starting signal. Now if I ask you to perform 2D DFT, 4D DFT or 4-point DFT, so I have to pad the signal with 3 zeros to make it compatible for 4-point DFT. Total factor matrix is given, 4-point we have already computed. So this is my signal, and if you see, I get this component. Okay, 2 2 2 2 2. So if I want to put it into the graph, it should be 0 1 2 3. So all will be having the amplitude of 2. Okay. So again, if I want to go back to the time domain signal, 1 by 4 conjugate of total factor matrix. If you see, the sign has changed. Then I have used this x of k over here. Just calculate it, and you get back to the x of n. Okay. So let us take an example of a signal x of n through 2. Okay. Now herein, if you see, if we perform 2-point DFT, we get a value of 4 0. When we go for the 4-point DFT, if you see, this 4 it comes here and this 0 it comes here, and 2 additional points it has come. Okay. In the 6-point DFT, if you see, we are here, this 4 we have got, this 0 we have got, but this 2 minus 2j and 2 plus 2j we did not get. Why that is so? Why that is so? Because if you go back in the total factor matrix, in the 4-point DFT we are having values at minus j and plus j, right? But in the case of 6-point DFT we are not having the value total factor values at minus j and plus j, and because of this reason, this computation, it is not giving us values corresponding to those minus j and plus j. In fact, it is giving us 4 additional values from the other regions. Okay, if you say, see, we are having these 4 additional regions apart from the starting 2-point DFT. So 1, 2, 3 and 4. Okay, so for 0 and this one we got this 4 and 0 from this 2-point DFT. Okay, but we did not get this extra 4 values. But when we go for the 8-point DFT, if you see, we got 0, 0, and from 4-point DFT we got this thing. Again, if you go for the 16-point DFT, all these points from 8-point DFT will be present over there. And if you go for 10, 12 and all these things, these values may be absent because they will not coincide. Okay, because they will not coincide. These total factor points, they will not coincide. Okay, so in addition to these 4 DFT points, we got another intermediate 4-point component. Okay, additional 1, 2, 3, 4 we got 1, 2, 3 and 4 we got, right? Because in the 4-point DFT we were having 4 values. At those 4 points we got the values, and additionally since it is an 8-point value, so in between those 8 points should be there. So those 4 values extra we got here. Okay, so what does this say? This says that if you want to convert this signal into 4-point signal, so we have to pad the signal with 2 zeros, extra zeros, and for those 2 extra zeros in the frequency domain we are getting 2 more extra points. Okay, similarly, if from the 4-point, if I have to go for 8-point DFT, I have to pad this 4-point signal with another 4-point signals. So I will be getting a matching 8-point signal component in the frequency domain. Okay, so what does this indicate? This indicates that in DFT, whatever is the length of your signal in the time domain, you will be getting the same length in the frequency domain. But the thing is that what is happening is that you are getting some intermediate values which were not visible in the low DFT points. Okay, low endpoints, capital endpoints, right? So padding of zeros, it is basically increasing the resolution of your signal. Okay, padding of 0, it is increasing the resolution of your frequency domain signals. Padding of the zeros in the time domain, it is basically increasing the resolution of your signal in the frequency domain. Okay, but please be reminded, padding of 0, it will not change the frequency component. It will not change the frequency component, but it will increase the resolution of the already existing frequency components. Okay, so you can look into this thing in a way that suppose you are having a window and you are standing at one side of the window and the window is totally closed, and on the other side you have an object which is covering this window size, or it is fitting with the window size. Now what I do is that, so this is a closed window, okay, blackened window. So from there I create two strips. So from these highlighted portions you will be able to see to that object. The object is already present over there, okay. So what you will be seeing, you will be only able to see only these two portions, the rest of the things you are not able to see. Now when I go for the 4-point DFT, I am creating two more strips, say one strip here and another strip here. So what will happen, you are again able to see this extra part, this middle extra part, okay. So padding of 0, what it is doing, it is whatever the scenery is already present in your signal, which is basically the frequency spectra, it is giving you the windows to look into the scene at a better resolution. Initially it was totally covered, but slowly you are able, by padding the zeros, by adding more zeros, you are able to see the spectra more clearly, okay. So these are the things, frequency resolution improvement. So all the examples are why it happens, these are given. So original DFT component is 0 padded DFT, okay. No frequency, new frequency components are produced. So these are some of the examples. The same thing you are given with the signal, you have to perform 4-point DFT. So you get to the XK. Okay, you have to compute the XK, then Xn, this is given, you have to perform 4-point DFT on the signal. So here only 3 values are given, so you have to pad it with a single 0 to make it compatible for a 4-point signal, and then you have to compute the X of k. Similarly, you can have question like this, Xn equal to cos pi n, perform 4-point DFT. So what you have to do, you have to find out the signal component for n equals to 0, 1, 2, 3. So here we are not directly saying that you only compute the 4 points. Here we are saying you have to do 4-point DFT. But if you go for computation of 4, 5 for cos pi n value for at 4, 5, 6, so it will make the signal longer than the 4-point DFT. So you don't need that, okay, because we are saying you have to perform 4-point DFT. That is giving you an indication that we have to stop at n equals to capital N minus 1, okay. That means 4 minus 1 is 3. So at n equals to 0, small n equals to 0, you have to stop, okay. So you have computed, then perform the matrix operation and you get this frequency. Then it may be asked that you perform the IDFT for a given XK signal. This is the method, 1 by capital N, 1 by capital N or conjugate of the total factor matrix multiplied by the XK value. Okay. Now coming to the fast Fourier transform. Fast Fourier transform can be carried out by 2 ways. The first one is decimation in time and the second one is decimation in frequency. So this architecture that has been given, it is nothing but your butterfly architecture. Okay, it is regarded as the butterfly architecture. So as it is, as you can see, it looks like something like butterfly. Okay. So here what we do is that we will be having 2 input components A and B. Okay, and we will be drawing 2 parallel lines. Okay, and these are the output points of this computation matrix. Then we will be having from this point to this point one value, this point to this point another value. Okay, so what this says, that this A, it will travel from here to this node, and this B will travel from this node to this node. So here in the first node, what we are having, A, then this B is coming to here, but before coming to here, we are having this total factor. It is getting multiplied with total factor. Okay, so we get A plus B total factor. Okay, and since we are having 2 points, so it is 0, 2. Total factor value is basically 0, 0, 2. Okay, then at the second output, what we are having, B multiplied by total factor, B multiplied by total factor. In between we are having a multiplier of -1, so we are having minus, and this A, it is coming over here. So at the second node we get A minus B total factor. Okay, so why it is done? This FFT is not a new transform. It is basically a methodology for implementing DFT in a faster way. Okay, so what happens is that in DFT we have a parameter called big O. Okay, it is regarded as big O. So big O means what would be there in the within the bracket. So that so big O means order of n square. Okay, so this gives you an idea of computational time. Okay, higher this value, higher will be the computational time. Okay, so if n is 2, so big O of 4, so the computational time will be 4. Okay, on the other hand, in the case of this Fourier transform, so if we see, we will be having big O of capital N multiplied by log of n. Okay, so if you replace this n with 2, and this log is log 2n, and we are having 2, so what we are having, if you see, this is 1, so we'll be having big O of 2. In the previous case, in DFT, we are having big O of 4. Okay, so what is happening? When n is small, the order of computation, it will be half of what we, in FFT, it would be half of what we were getting in the case of DFT. Okay, because it was 4, so this is for DFT. So computational complexity will be, in DFT it will be twice of FFT. Okay, so it will be taking twice the time to achieve the same computation. Okay, now if I increase this n to 4, so what will happen? N square 16 for DFT, and for this one log 4 2. Okay, so it will be 8. Again, if you see, it was only, see, there was not much difference with time, but if you see here, it has become a difference of 8, and we are only talking about 2 and 4. You consider the thing when we are handling thousands of data, because we said that what we are having in a second for ECG signal, what is the maximum frequency we discussed? We discussed that the maximum frequency is 150 hertz. So what would be the minimum Nyquist rate or Nyquist frequency? It should be 300 hertz. So in 1 second we will be having 300 data points. So you look into the number of the data points. So here it should be 300 square, okay, and in the case of other one it should be 300 multiplied by log 2 300. So you compute, so it will be far lesser than the big O of the DFT. Okay, so it shows you the computational complexity. Now why we don't go for say actual computational time? The actual computational time will depend on the processor. Okay, if you see some computation in your computer it may be slow, but in my computer if I am having a bigger processor with very good RAM, so it will be quite fast. Okay, now what this BIGO does, BIGO helps us in comparing the thing, in comparing the computational complexity, where if we consider that our system remains the same. Okay, and that is the main advantage of BIGO. Okay, so from here we can see that FFT can allow us in handling a larger number of data set at a much lesser time. That means the computational complexity decreases. Okay, now the how it achieves a superior computational time. It works on the rule of divide and conquer. Okay, how it works? It works on recursive decomposition of the signal. Okay, and then it finds out the DFT for those small segments and then combines the results for each of the small segments. Okay, so I will show you how it is done. So we are having this signal over here, and say for example it is having a length of 8. So we are having values from x of 0 to x of n. Now what I will be doing, I will be decomposing the signal. So what I am doing, I am taking all the even components at one side and all the odd components on the other side. Then again I will be taking the even components from here and odd components here. Similarly over here. Now if it is 16 point, so at this stage we will be having 4. Again we will be having further round of decomposition. So what it is doing basically, we will be decomposing the signal until and unless we get a pair of signal components. Okay, we get a pair of signal components, and once we achieve that, now this series x0, x4, x2, x6, x1, x5, x3, x7, it becomes the input combination for the FFT algorithm. Okay, it becomes the input sequence, for the FFT algorithm. Okay, so in the case of butterfly architecture, here we are having 2 points. So we will be having x of 0 and x of 1. It is at the lowest pair. Okay, so only one pair is there. So for the 2-point DFT, we'll be having x0 and x1. Okay, and since we are doing this, so we get 0, 2, and we perform this computation. But in the case of that, we do it for the computation. In DFT you are doing the matrix multiplication. It was more cumbersome, so we do the butterfly, we implement the computation in the butterfly architecture, so that our number of computations it reduces. Okay, and it becomes n multiplied by log 2n. So we already discussed for the 2-point system. Okay, now in the 4-point system, what happens? We are having 4 signal components: x0, x1, x2, x3. So we'll be taking x0, x2 together and x1, x3 together. So it becomes my input sequence. Now if you look into the input x0, x2, x1, x3, what does this mean? I will use this butterfly sequence to perform 2-point DFT first. Okay, so we are using 2-point. So see, we are having this butterfly architecture. So at the top point, if you see, there are no total factor. Only at the bottom I am having the total factor. Okay, here also for x1 and x3 I will be performing this computation, the same computation. Okay, so what is the midline over here? Midline is here. So this is an imaginary midline. Okay, so for this I am having this midline, and for this one I am having this midline. So you need to keep it in mind, if it is a 2-point DFT, in the first part we are not having total factor, we are having total factor in the second part of the computation, computational pipeline. Okay, when we go for the 4-point DFT, what is the midline? It should be after 2. So after 2 lines, here and here, we are getting the midline, and then we are having the total factor W04 and W14. Okay, now if you see, we have got here A and B. What is A? A is nothing but x0, directly it is coming from here to here, plus W02 is 1, x2, there is no multiplication, so x0 plus x2, A. In the case of B, we are getting x0, this x2 is multiplied with -1, so we get x0 minus of x2. Okay, similarly over here we get C and D. Now you see, from the top line we will be doing an exchange of the information from top line of the first half to the top line of after the midline. Okay, so from here to here we are getting this exchange of information, and from here to here we are getting this exchange of information. From first line to first line, again from second line to second line, it will be happening. And where will be our total factor matrix? Total factor points. Total factor points will be after the midline. So it is a 4-point DFT we are performing. So we get W04, W14. The values would be there. Okay. So once you are having this, so what happens? If you see x of 0, A, it directly comes over here, and C, it gets multiplied with 1. W04 is 1. It comes over here. So we get x0 as A plus C. Okay. And if you look over here, we get x2 equals to A minus C. Okay. Similarly for the x1 and x2. Now if you see, our input, it was in the decimated form. It was in the decimated form. However, our output, if you see, it is in the normal order: x0, x1, x2, x3. Are you getting my point? So input is in the decimated form, output is in the normal form. Okay. Now if I have to do inverse DFT, I have to take this xk value in the decimated form in the input size. These total factor values, they will become the conjugate values, Okay, then you will be getting over here x dash 0. Why I am saying x dash 0, x dash 1, x dash 2, x dash 3, because I have not multiplied these values with 1 by capital N. So after multiplying it with 1 by capital N, we will be getting x0, x1, x2, x3. Okay. So this is the 8-point DFT. I will take an example first, and then we can go for this one. For the 8-point DFT, if you see, our signal is 0, 1, 2, 3. Okay, so it should be in the decimated order. See, 0, then 2, then 1, 3. So this is 1, this is 1, minus 1, minus 1. So here what we get, 0 plus 2, we get 2, and here we get 0, 2 multiplied by minus 1, 0 minus 2, or minus 2. Okay, similarly over here we get 4, and here we get minus of 2. Then again, this is the midline. Information flow is from top line to top line, again bottom line to top line to top line information flow. And this is W04, this is W14. So 1 minus j. So again, if you see, at this point what we are having, we are getting this 2, and here we are from here we are getting 4 multiplied by 1, 4 plus 2, we get 6, and at this point we get 2, then this 4 is getting multiplied with minus 1, 2 minus 4, minus 2. In this way we get these values. So this is x of 0, this is x of 1, x of 2, x of 3. Okay, so our answer is this. So now if I have to do the IDFT, what I have x of k equals to this thing. Now what should be my input sequence? Right? Same methodology, and we get x dash n, which is in this format. Then I will get x of n, this one divided by 1 by 4. So I started with 0, 1, 2, 3. So I got 1, 2, 3, 0, 1, 2, 3. Okay. So in the 8-point FFT, what we did, you see, up to this point it is the same. It is the same here, and also the same thing is repeating over here. So W08 and W28 are they and W04 and W14, are they same or not? W28 is equal to W14. Why? Because we were having NK divided by capital N. So NK is 2, 2 by 8 is equal to 1 by 4. Getting my point? So for the sake of understanding, you see, I keep that in mind when I go for this. Otherwise what happens now, if you want to remember it in 08 and this form, so it becomes bit wonky. So see, 0 then 2 8, okay, you may get confused. Okay, so this is equal to 02, this is equal to 02. Okay, similarly over here we got since we are doing 4-point DFT, W04, W14, here also W04, W14, and when we are doing 8-point DFT, I prefer W08, W18, W28, W38. Okay, so you need not to remember this jumping of the total factors and all these things. So in this way, should be able to compute the thing in a easy way. Okay. So this is it. And another important thing, this order which we created, it is also regarded as the bit reversal order. Okay. So in the bit reversal order, what happens in the natural order? We are having x0, then x of same up to 8, 7 we are going. So we can represent it with 3 bits. So x of 000, then 1 it is represented at 001, then 010, in this way. In the bit reversal order, what we are doing, this least significant bit we are making it as the most significant bit and vice versa. Okay, and the middle one it remains the same. So it seems 001 it becomes 100 because 1 comes over here and this 0 it comes over here. So again, if you go for the decimal points, so x0, x4, so it is in the same order. Okay, in the order where we decimated the signals and got the order. So hence decimated order or bit reversal order, both are regarded as the same. So with this I will stop here. You can look into this table. So but I found that student don't find this one useful. What I have done is that many times I found at initial stages when I started teaching, student used to do mistake. So while computing the butterfly, so I made this table. You will not find this table anywhere else. So we made this table saying initially we are having 2-point DFT. So you just have to put the values, then W and total factor for the these values. Yellow cells we need to put the total factor values. Okay. Then we got the output. Then in the second stage we were supposed to do the 4-point DFT. So after the midpoint we are having the total factor values, and here the outputs are in the same way. Okay. So it's just the tabular form of representation of what we did in the butterfly architecture. So whatever you can go through my previous year's lecture. Since your classes started quite late, so I am not going into the details because it will consume almost 15 minutes to 20 minutes. Okay, so you can go through the 2024 lecture. Over there, I have made it. I have explained it, and you should be able to understand it properly. If you face any trouble, you can come back to me, and I will be happy to help you. So with this, since we are decimating the order in the time domain, that means in the input sequence, hence it is called DIT-FFT. In our next class, we will be looking into the DIF-FFT, where the output is decimated in the decimated form and our input it is in the normal. Okay. So with this, we stop today.